All right. Well then, let me say a few words about definite integrals. And that again is only technical thing that you'll have to practice for computations. Let's say I want to integrate, and I would like to do it successfully. So I will choose something I know will work. Let's say x times e to the x squared dx. Again, you may notice that if I remove that x, the antiderivative cannot be expressed in any reasonable way using any function you know, right? It's that urfi function of x, as Wolfram alpha suggests. But if I multiply by x, I can do a substitution. But now I would like to integrate, say, from 1 to 3. Or maybe from 2, to emphasize the difference. So I want to integrate from 2 to 3 that function. And one way to work it out is finding indefinite integral first. So let me find indefinite integral. And I will do it by a substitution. U equals x squared will work because the exponential part is clearly a function of u, a very simple function, and the remaining part, x dx, looks like the derivative of x squared multiplied by dx. It looks like du. So du is 2x dx. Up to that constant 2, I have a product of a function of u times du. And that's exactly what makes this substitution work. So I have e to the power u times x dx. X dx is a half du. Now I can finish the integration. Antiderivative of e to the u is e to the u again. And once I found this antiderivative, I can compute the definite integral. I can write it as well, here's the step I haven't finished. I haven't converted the antiderivative into a function of x. So it is a half of e to the x squared plus c. And now you can use that antiderivative, 1/2 e to the x squared, to compute the definite integral. I have to substitute 2 and 3 and subtract. So I have substituting 3 e to the power 3 squared minus a half of e to the power 2 squared. So it will be a half of e to the 9 minus e to the 4th. All right. So one way of doing substitution is forgetting for some time about definite integral, completing indefinite, and then using it in the computation of definite. Another way, and the difference is just technical difference, and it's up to you which way to prefer, but please don't mix them. So another way is to work directly with the definite integral. So start with the and now when I do the substitution, u equals x squared, I find my du, and I work with the integrand exactly the same way. So I say that this is e to the power u times 1/2 of du. But now I have to make that a definite integral, because I started with definite integral. Now, if the limits for the variable x are 2 and 3, what do you think the limits should be for the variable u? 4 and 9. So for the lower limit, you put u of 2, u of this limit, right? And that happens to be 4. For the upper limit, you put u of 3, and you compute it using this substitution formula. Well, you introduced yourself. And I end up with a definite integral from 4 to 9 of a half of e to the u du. And I don't have to go back to the variable x. Because what I'm looking for is the number. I'm not looking for a function. My answer is going to be a number. Now, this number depends on u only. There is no influence of x. I don't need x anymore. And I find antiderivative. I substitute 4 and 9 instead of u. And I get a half of e to the 9 minus e to the 4. Now, the typical mistakes is about mixing these two ways. And proceeding with this computation of definite integral and then substituting the value of x in there instead of u. Right, so you have to be clear about whether you're working with the old variable x or the new variable u. Whether you convert everything into u language or you stay with x all the time and then use those limits for x. But otherwise, if you don't mix, it's up to you what to choose. And of course, it only matters in long computations, right? When you have to do a substitution, then trigonometric substitution, then integration by parts, substitution again, right? So then you may want to avoid coming back to the old variable because you don't need it. And otherwise, if you try to find antiderivative, you will have to drag that old variable all the way to the very end.